All right, so let's look at lab number 11, which also deals with digital circuits. And in the last lab, we had looked at uh, basic gates and also combinational circuits. So in this particular lab, we'll look at building blocks of sequential circuits. So we'll start with a latch that can be implemented using Nand, two Nand gates cross-coupled in this particular manner here. And we could also build it using a NOR gate as well. And so this is a SR latch, and the behavior of this SR latch is shown over here. So S, for setting the latch value equal to 1, and R is for resetting the latch to 0 value here. So when you put S equal to 1, R equal to 0, you get Q and Q bar here, which is 0 here. So we call this the set inputs here. 0, 1 will reset it, and 0, 0 here, the latch will maintain its state. Whatever is, whether it's in Q is 0, so it will remain 0, Q is 1, it will remain 1 here. So this is called the hold state here. And 1, 1 is we consider it as an invalid set of inputs. We'll see that many times when you have 1, 1, and then when you go to 0, 0, the output is unpredictable. And we'll see that through simulations that is there here. So what we would like you to do is use the simulator to study this SR latch here and its behavior described by this table here. And also understand why, for example, the 1, 1 input is not allowed here. And so this is a latch which is implemented using NAND gates. We would like also you to implement a latch using NOR gate and studies behavior as well. And in the next part, we'll look at a flip-flop, which is a edge-triggered latch here. So we call it a flip-flop here. So this particular circuit acts like a positive edge-triggered flip-flop. So we'll look at how this particular circuit behaves. We'll try to understand it again using our simulator. And then our simulator allows, it has this block which can act like a Dflipflop here. So we'll study its behavior, this particular one. And then we'll use these Dflipflops to make a circuit which goes through a set of fixed set of sequence of binary numbers here. So it's basically like a counter. And so we'll see, we can use, we'll take this particular circuit and simulate it to understand the sequence of numbers through which this particular circuit goes through. All right, so with this background, let's open up the simulator. All right, so this is the first part of the lab here, where we have this NAND latch here. And these elementary gates we had seen in the last lab, these are available in a library here. So we could select. And to apply input to this SR latch, we've used a 2-bit stimulus here, right? 2-bit stimulus. So it will have 2 outputs. And so it's a convenient way of applying the stimulus here. And what we want to do is basically, before that, we want to go through these different states that are there here. We would like to apply, let's say 1, 0, 0, 1, 0, 0, 1, 1. We would like to go through all of these inputs here and see how the latch behaves here, right? So with that in mind, so it starts at 0 nanosecond, we'll apply 0, 0. So 0, 0 is the hold state. After 50 nanoseconds, we'll apply 0, 1, right? So 0, 1, note that 0, 1, which means set is 0 and R equal to 1 here, right? So 0, 1. Then we'll apply 1, 0. Then we'll apply 0, 0 here, and then 1, 1, and back to 0, 0. We'll see all of that. Okay, so you can apply any set of inputs you can generate with an interval of 15 nanoseconds here, right? Okay, so let's simulate it. Analysis, you have to do transient simulation. And we are going to look at the digital or the state of the line S, line R, line Q, and line Q bar. Q is here, Q bar is here. So we'll look at all these states. S and R are the inputs, and Q bar the outputs here. All right, so we'll look at that transient limits here, and we'll simulate it for 500 nanoseconds. Note that the inputs are changing after every 50 nanoseconds, so let's run it. Okay, so this is what we get. We can put a cursor here. So we start with the 0, 0 input. Note that S is 0. So let's look at the left one here. S is 0, R is also 0 here, so 0, 0. And the latch is, when you switch on, let's say a latch, you don't know what state it is in. It could be in 0, 0 state, it could be in 0 state here, 0, 1, or it could be 1, 0. We don't know. So right now it's just X value here, unknown state here. So unknown state here, and then here, right here, the latch now changes state here, right? So we've applied, so because 0, 0 was a hold state here, so that's why nothing was changing here. Note that 0, 0 is the whole input, is a hold state here. So the latch stays in an unknown state, XX here. Next, the input changes from 0 to 1. So 1 is a reset input here, so that's why Q goes to 0, and Q bar obviously is 1 here, so it stays there. Next, the input that we have applied goes to 1, 0 here, so it goes to, output goes to 1 and 0 here. So this is the set input here, right? And then we go to 0, 0, so the output stays in the same state here, 0, 0. Now we come to the invalid input, which is 1, 1. So you can verify that 1 and 1 will put output Q to be 1 and Q bar also to be 1. Both of them become 1. So in one sense, it is sort of an invalid input because we expect QB to be complement of Q here. So that rule is getting violated. But more than that, when you go from 1, 1, when you go from 1, 1 here, and then you go to 0, right? So let's say 1, 1, and then input you change to 0, 0, right? So we'll do that. So it goes into 0 and 1. It goes into 0, 1, right? So 1, 1, normally when you go to 0, 0, we expect the latch to hold a state here. So first of all, it's not holding a state. And the second one is going to 0, 1. Now this is where there's a problem. It goes to 0, 1, and this state 0, 1 is unpredictable. We'll show you is unpredictable in the sense that it depends on, for example, which gate, let's say, is faster. So if you go back and look at this particular gate, so this particular gate typical delay is 1 nanosecond, both high to low and low to high, 1 nanosecond. The other one, the other latch, the other gate here, we have made it a little faster, 0.9 nanosecond here. So it's a faster gate. So when you apply 1, 1 here, when you apply 1, 1 here, and the output is 1 and 1 here, and then you go to 0 and 0, 0 here, it depends on which gate is faster. So right now this gate is faster, and that's why we are getting the output here as 0 and 1. Note that 0 and 1 here. But let's make this particular gate slower. Let's make this gate slower. So I'm going to increase it to, instead of 0.9, we'll make it 1.1. 1.1 nanosecond, and both of them 1.1 nanosecond here. 1 nanosecond here, right? And then let's simulate, and then you'll see the behavior here. So let's put a cursor here and let's go back here. So note that the output has become 1 and 0 here at this particular point. 1 and 0 here, right? So, when you go from, when the input is 1 and 1, the output is 1, 1. When you go to 0, 0, the output becomes Q equal to 1 and Q bar equal to 0 here. So in addition to the gates having different delays and that determining whether the output goes to 1 or 0, a similar thing would happen depending on which input arrives faster. For example, if this one arrives faster as compared to this particular input, then you will get some one particular kind of behavior at the output. On the other hand, if the other input arrives faster than this one, then you'll get a different kind of an output. And this is what makes the behavior of this particular circuit unpredictable, because in general we cannot control which gate will have a delay a little bit more as compared to the other. And similarly, these inputs are coming from some previous gate, so we cannot control precisely that both the inputs should arrive at the same time, or one should be faster as compared to the other. And that's why when we go to 1 1 state here, and we get a 0 0 output at the output here, but then the subsequent state becomes unpredictable, especially if we go to 0 0 here, because it's not able to hold the previous state, and the state is also unpredictable. So that's why we avoid this particular state altogether here. So anyway, this is a NAND latch, and you can implement similarly a latch using NOR gates. And also what you could do is you could add a enable input here, so that the latch only works when the enable input is 1, let's say. Then the latch is enabled and it will respond to the inputs. On the other hand, if the enable input is 0, then the latch is disabled, in the sense that it will not respond to any changes in the input, and it will simply hold the outputs into whatever state they are in here. So this NAND latch is a basic unit of memory, and however, it has problems, and a better elementary memory circuit is what we call as a flip-flop, and a flip-flop responds only to an edge of a clock here. So one example of a flip-flop is shown over here. So this particular circuit is a positive edge triggered flip-flop here, consisting of 6 NAND gates cross-coupled in this particular manner here. So what we would like you to do is understand the operation of this particular NAND gate by simulating it here, right? So flip-flops are clock-driven. So this is where we apply the clock here. So you can select the clock from the stimulus generator here, right? So there is a D clock here. So this is the clock that you can select from here. And if you double click, the clock requires you to define its time period here. So 0 width and 1 width. So is 0 for 500 nanosecond and 1 for 500 nanosecond, which means that the total period is 1 microsecond here. So it's a 1 megahertz clock here. And this is where we apply the input to the Dflipflop here. So we've applied the input here. It starts with 0. After 100 nanosecond, it goes to 1. And after 800 nanosecond, it goes to 0 here. So that's the input here. And so let's simulate it and see whether it acts as a positive edge triggered Dflipflop here. So let's do a transient simulation again. And in this case, let's disable the previous circuit and enable here D clock and the D input and the Q input here, right? So let's do that here. And let's simulate it for 2 microseconds here, because our clock period was, or we'll simulate it with more depending on here. So all right, so let's put a cursor here. So it starts off by our flip-flop is in unknown state here, and the moment note that then what happens is we have taken the input D, we have made it 1. We made it 1, but the output will not change here, right? The output will only change after the positive edge triggered here. So this is where, for example, we get a positive edge. Clock goes from 0 to 1, and the output here responds to the input here and becomes 1 here. But note now, we have taken the input, D input, and made it 0 here, but it's not responding. The output does not respond to that. There is a clock edge here going from high to low. It doesn't respond yet, right? So it's only when the positive clock edge comes, then only it responds, and then it becomes a 0 here, right? So this is how a positive edge triggered flip-flop is supposed to work, and we can verify its operation of this particular circuit through this particular means here. So if you wish, you can go ahead and monitor all these different lines that are there here, and you can see how it is how it's becoming a positive edge triggered flip-flop here. So so this is implemented using these NAND gates here. And our simulator has in its library a flip-flop, a Dflipflop already available. So you don't, when you're implementing more complex circuits, you don't really have to implement a flip-flop using elementary gates. There's already a block which acts as a flip-flop here. So this will be there in your here in edge triggered flip-flop here. So they have a JK flip-flop and a Dflipflop here. So that's what we will describe here. So this is this particular circuit here. Dflipflop here. This is the clock input here. This is the D input here. This is the output here. And it has two additional inputs called preset and clear. And these are asynchronous in nature. Asynchronous meaning that it doesn't depend on the clock. Normally, the output here responds to the input only when there is a positive edge comes. Then only the output will change in accordance with the input. So that's we call this a synchronous operation which synchronizes with the clock here. On the other hand, this one, these are asynchronous inputs, and you can is sort of clearing the flip-flop or setting it to a particular value. For example, if I put it here 0 here, and analysis say dynamic DC. So note that it will make it 1, right? On the other hand, so this is active low. So only when you apply a 0 here, then it will clear it. Sorry, it will set it to 1. Note that again, if I put it 0 here, it will set it to 1. On the other hand, the moment I put it to 1, well, then it goes back to its distinct state. So similarly, this one, for example, will clear it. If you apply a 0, for example, here, so this will, if the flip-flop were in a state of 1, then this 0 here would clear the flip-flop here. So these inputs, they work independent of the clock, right? So they do not depend on a positive edge or a negative edge. They only depend here on this particular one. So normally you have to keep these inputs to be 1 because these are active low. There's a bubble here and a bubble here, active low, which means you have to keep them inactive. And you do that by applying a 1 to both these inputs here. So anyway, just like in the previous circuit, you simulated this particular circuit to understand that is working like a positive edge triggered Dflipflop. Similarly, you can simulate this particular circuit here, this block here, and see that it acts as a positive edge triggered flip-flop here. And in the last part of this particular lab here, what we can do is we can take a couple of these flip-flops that are there here. We've taken 3 flip-flops and it's connected in a particular manner here. The output of the first flip-flop is connected to the input of the second. The output of the second flip-flop is connected to the input of the third. And the complementary part is connected back to the input here. So this circuit acts like it's like a counter, and it's a synchronous counter. The same clock goes to every flip-flop here. The clock is over here. And what you can do is you can simulate this particular circuit to see what are the different states through which this particular circuit goes through. So as usual, you'll have to do transient simulation and then look at the output Q4, Q5, and Q6. Okay, so let's do that. Let's do transient simulation here. And let's disable this here. Let's focus on those outputs here. So we have, all right, so we have Q4, Q5, Q6, and the clock here, right? The clock is here. So let's run it. All right, so we have run it only for 2 microseconds. Maybe let's run it for a larger period here, 10 microseconds. All right, so then you can see the different states through which it goes here, right? So this is the clock that is there here. So clock comes here, the system goes into a 100 state here. Then the next edge clock comes here, it goes to 110. So it goes from 100 to 110 to 111, then 011, 001, 000, then 100, 110 here, right? So it goes through. So you can look at the sequence through which this particular circuit goes through. And so this is a counter, but this is not like a normal binary counter. So it goes from 000 to 001 or 010, systematically from 0 to 5 or 6 or whatever. It goes through some sequence, right? And you can simulate it and find out what the sequence is for this particular circuit here. So this is a clock again, clock with 1 microsecond time period here. And what we would suggest is that you take these three flip-flops and try to construct different kinds of counters. For example, a counter which will simply go from 000 to up to 7, 111, and then back again. So you can call it an up counter, starting from 000 to 7, and then back again. Or you could do a down counter, which goes from 7 and goes backwards. So 7, 6, 5, 4, 3, 2, 1, and 0 here. So you could down counter and maybe counter which goes through only goes from 0 or goes from 1 to 3 to 5 to 7, only the odd numbers or only the even numbers. So try designing different counters and implement it using these Dflipflops, and then you can simulate and check that your design is proper here. All right, so that's part of lab number 3 here, lab number 11 here. And so these are the three, basically 4 parts here. The first part is becoming familiar with Nand and NOR latches. The second part is looking at one particular implementation of a positive edge trigger Dflipflop, and then using a block in the simulator which acts like a Dflipflop, becoming familiar with it, and using that as a unit to implement counters, different kinds of counters that are there here. All right, so please note that there was an error in this particular table here for 1 input. It was written here 0 0, but as we saw in the simulation, when you apply 1 and 1, it is 1 and 1 at the output here, right? So which is obvious that when you apply 1 and 1 here, the output here, here is 0 and 0, and it will set both the NAND gates to 1 and 1 here, right? So it was written for a different circuit here, 0 and 0. So please correct that. When you apply 1 and 1, you get output also both Q and Q bar is 1 and 1. And as we discussed in more detail, that when you go back to 0 and 0, it doesn't stay at 1 and 1, but it goes to an unpredictable state depending on which gate is faster or slower, or which input arrives faster or slower here. Okay, all right.